Hello everyone, welcome to our Data Structures and Algorithms Concept series. In this video, we will understand the queue data structure with some real-life examples and types of queues, implementation of queue, and performance of different data operations using queues, so that we will get an idea about how queue data structure behaves with the different data operations and depending on the different problem statement, whether we should use queue or not. That will help us to decide. So let's start. Let's understand the queue using real life example. When you go to the movie theater, you can observe the line outside the ticket counter. So the person standing at the beginning of the line represents the front of the line, and the person who is standing at the end of the line represents the rear or end of the line, right? The person who is at the front gets the ticket first and moves, right? And the next person becomes the front of the line, right? And if any new person is coming to get the ticket, stands at the end of the line, right? So this represents the queue data structure. So basically, as we saw, it is a linear data structure as each element is connected to one element. And it follows the first in first out principle. The person who was at the front got the ticket first, and the element is removed from the front or the beginning, and that operation is called as a DQ. And if any new element or item gets added to the end, and that operation is called as a NQ, right? So let's understand the different types of queues. So first type is a simple queue or linear queue. It follows the basic first in first out principle, where you NQ at the end and the DQ from the front, right? So there are some problems with the simple queue or linear queue. Let's understand. So here you can see that we have the queue represented by array of size 5. Front is at 0 and rear is at 4. So when we DQ, right, in a simple queue, what happens that all the elements are actually shifted to the beginning again. So front does not move, all the elements are shifted to the beginning. Why front does not move? Because if let's say we remove 5, 7, 9, 11 and front comes to the 15, then all the elements which were removed, this space is now empty and wasted, right? So to save this wasted memory, the expensive operation of shifting is performed so that whoever new element comes can be added at the end easily, right? And the rear changes based on the element added or removed, right? The front does not change. So this is the problem with the simple queues, and these are basically handled in the next type of queues, right? So the next type of queue is a circular queue, which overcomes the limitation of the simple queue by treating end of the array as connected to the front. We'll understand it how. And it uses the front and rear pointers with a modular arithmetic, right? Let's understand with the example. The same example with the array of size 5. Front is at 0, rear is at 4. So when we do DQ, the front goes to the next position using modular arithmetic. The front plus 1 modular capacity. Capacity is a 5 here, the size. 0 plus 1 modular 5 is 1. It's basically the remainder, right? So front goes to the 1, and you can see that, let's say, new element comes. In simple queue, if the new element came, we had to shift all the elements before that, right? In a DQ, then only we could add the 17 here. But here, the rear is incremented similar to the front, like rear plus 1 modular capacity, 4 plus 1 modular 5 equal to 0, right? Now rear points to 0 and 17 can be inserted at the rear position, which is 0, right? You can see how the circular queue overcame the limitation of simple queue by treating the end of the array. Basically, rear was pointing at the end, but it shifted to the beginning of the array or front of the array using the modular arithmetic, right? The next type of queues are priority queue and double-ended queue. So priority queue does not follow the first in first out. It follows the priority based DQ, right? The elements are removed based on the priority. It can be high priority queue or low priority queue depending on the problem requirement. It is implemented by different data structure. So we'll cover this in another video. Double-ended queue is basically allows the insertion and deletion from the both the ends, right? So it provides the capability of both queue and a stack. So both of these queue types we'll cover in another video in a detail. So let's understand the queue implementation. So most modern programming languages provide an inbuilt support for a queue. internally queue is implemented using either circular dynamic array or linked list, right? Dynamic array is basically when your array is full, it automatically internally programming language resize it using a growth factor. To understand the dynamic array and its resize, you can check our array data structure related video. And circular because we want to optimize or overcome the limitation of simple queue, which we discussed, right? For languages like C, which does not provide inbuilt support, you can still implement using the static array, but it will be the same problem as we face in the linear queue, right? There are different types of queues and their implementation might have some tweaks, but the base is array or list only, right? So let's understand the queue implementation using array. So let's say we have the queue with an array of capacity 5. Count is 0. Count represents the number of elements. Front and rear points to -1 because no elements are here. When one element is added, front and rear are pointed to 0 position. Count is 1, number of elements. Capacity is 5 because capacity is still 5, right? Not changed. New element added, front stays at the beginning because it's an NQ operation, so rear will change. So as NQ happens, rear goes on incrementing, and when the rear points to 5, the count is 5 and capacity is 5, so queue is full, right? So in case of dynamic array, the resizing will happen and the array with more size will get allocated and these elements will move to that new location, right? So it's basically the resizing of the dynamic array, but it happens very rarely because programming languages handle the dynamic array resizing very smartly, right? Now, in this case, there was no free space available to insert a new element. That's why the queue was full and resizing happened. But what if there is some space? Then how that new element can use that space, right? Let's understand. So let's say we have this same array where there is no space for new element. And let's say if some DQ might have happened. Let's say 5 was deleted, then front will point to the 7, which is at index 1. Count is 4 because now 4 elements are only there. Let's say like this 5, 7, 9 got DQ'd. Front is now pointing to 3, which is at 3 index, which is at 11. Count is 2 because only 2 elements are here. Rear is pointing at the 15. Now if we say NQ17, now when as we saw in a previous slides, right, how the rear comes from end to beginning to utilize this free memory, right? So rear is equal to rear plus 1 modular capacity. So modular arithmetic is used. 4 plus 1 modular 5, which is rear 0, right? Rear will come to 0 from end, it will come to beginning, right? Count is less than capacity, so only 2 elements are there, so we still have some free space here to insert, right? So it will insert 17 at the new 0 position of rear, right? This is how the free space is utilized, and rear came from end to beginning to utilize that free space, right? Now this while doing NQ, we saw how rear comes to beginning. What happens while doing DQ, right? Let's understand that with the same example, right? So let's say now front is pointing at 11, index 3, rear is at 0, which came back here after adding new element 17. Let's say we DQ, front goes to 4th index. Now when we DQ again, 4th removes the 15. Now where will front will come, right? Front will come to the beginning. How? Using modular arithmetic. Front plus 1 modular by capacity. 4 plus 1 modular 5, which is again comes to 0. So front will point to 0, rear is already at 0, and count is 1. Now the number of elements is decremented, right, after DQ. So now when we try to DQ, it will DQ 17 at a number with basically the number where front is pointing. So it deleted that item like properly, right? So we saw from end how the front also came to beginning, right? So now count is 0, it means queue is empty, so no more DQ is allowed. So we saw how the front and rear are moved from end to beginning, and how the free space is utilized, and how the dynamic array can be used to resize the array for this queue. Now let's understand the queue using linked list, right? So the linked list node is represented with this object. Int value is the value stored in to that node, and the node next is basically the reference to the next node, right? Let's understand it. So initially the front and rear will point to the null pointer. There are no elements. So when we say NQ5, the new object will be get created with value 5, and next value will be null, right? There are no more nodes. So front and rear will point to this reference of node 5 object, right? When the NQ7 happens, you can observe that the next of 5 node is now pointing to the reference of new node, which is 7, and rear moves to the 7 node because rear points to the element which is added recently, right? And the next of 7 is null because there are no next element here. So when we do 9, you can see the rear goes to the 9, and the next of 7 changes to the reference of 9 object, right? And when the DQ happens, the front, basically this front node will be deleted, and it will point to the next of the node which got deleted. The next of node is reference of 7, right? So it will point to the 7. Front will point to 7, and rear is at the 9th node, right? Node of value 9, right? So we saw the implementation of queue using array and linked list. In most of the programming languages, the queue is implemented using dynamic array because of the cache efficiency and very smart way to resize the dynamic array, and less for a memory overhead compared to the linked list, right, which is maintains the next pointer and all those things, right? Let's understand the different use cases, right? So the use case where order preservation or the ordering matters and efficient sequential processing is needed, right? For example, let's say you are in college and you want to print something, right? And there are other students also who are basically sending job to the printer, right? So all these tasks are basically added to the queue by the printer processor, right? So that the printer functionality can be given to each task, but giving priority to the, or basically the task which came first, it will process that task first or print that task first, right? So it is nothing but the ordering is maintained and the sequential processing happen based on first come first serve using a queue data structure, right? There are more examples like how the CPU schedules our job so that we can run different applications on our computer, concurrency and multi-threading. And similarly, the call center management, like let's say if you call to any, let's say passport office, right? It will say you are in a queue, right? Just like that. Then use case asynchronous background processing. Here, if you can see, what does that mean? Let's say you are uploading some YouTube video, right? So it will internally, you will see that it is uploading. What it does basically, it puts your video or that task in a queue, and the video upload service onto the YouTube will read the task from the queue and actually upload to the YouTube, right? You don't need to worry about it. So all this background processing is happening asynchronously. You are not blocked because of it, right? So this is this asynchronous processing is handled by the queue in between, right? So similarly, the similar example for this is order processing e-commerce, right? When you order something and that order processing, basically which order where to deliver, all that processing is handled using queue in the e-commerce order processing service, right? Now let's understand the different data operations on a queue. Adding an item at the end, right? So if you see here, if we try to add a new item at the end, and if we still have a capacity, let's say if we have a capacity of 10 here and only 5 are added, it can be added immediately because queue offers the NQ at the end, right? So it is very often. Now it is amortized because if suppose it is full capacity, reaches full capacity, the array resizing will take some time, right? Now adding an item at any place except end. So here, if you see that if you want to add any item, let's say 15 between 9 and 7, right? We need to dequeue the 5 and 7 and put it into the new queue, and QB, and then QA will look like this, right? 5, 7 are marked deleted, front move to the 9 index of 9, right? To basically index 2. And then we add a 15 to the QB, not to the QA, and then all the elements from QA moves to the QB. So it will look like this, right? And the QA is removed and QB will be the new queue now, right? So you can see that in a worst case, it will have to move all the numbers, all the elements basically, right? So that's why the performance is O of n. N is the size of the queue, right? Deleting an item at beginning. So because queue offers the dequeue operation at front, so if we remove the element from beginning, it will basically O of 1 very fast, right? But deleting an item at any other place except at the beginning, it is similar to the insert data operation, right? Except at end, right? So dequeue the element 5 and 7, put it into the new queue, dequeue the element 11, dequeue the element 9, and push all the elements from original queue to new queue, right? Make the new queue as a original queue, right? Here dequeue element, instead of 11, it is 9. Sorry for that. That's why the performance is often similar to insert, because it will have to move in worst case all the elements, right? Search an item. Now in this case also, like if you want to search 15, you will have to parse whole queue, right? That's why the performance is O of n. And when we want to access an item in a queue, basically if we access the element at front or rear, then it is O of 1, because we have these methods are exposed. In some of the languages, the access element at rear is not exposed. For example, C#. So there it will be of 1 n. But in most of the languages, it is exposed. That's why it will be of 1, right? But if we try to access the element at any other place, the performance will be O of n, right? So we understood the queue using real life example, different types of queues, how the queue is implemented internally, and what are the performance of different data operations on a queue, and what are the use cases. So hope you understood the explanation and got the knowledge about in what cases what use cases the queue can be used, and what is the impact on different data operations when we use the queue data structure. If you like the video, please share and subscribe. Thank you. Hope you understood the explanation and what is queue data structure, different types of queue, and its implementation, different use cases about the queues and its performance on different data operations. So it will help you to think in the right direction for different problems. If you like the video, please share and subscribe. Thank you.